बिस्मिल्लाहिर्रहमानिर्रहीम रब्बिश्रह ली सदरी व यस्सिर ली अमरी वहलुल उक़दतम मिन लिसानी यफ़क़हू क़ौली. Assalamu alaikum. Today we will do quantum mechanics by Beck, example 1.4. Find the eigenvalues and eigenvectors of matrix M bar. M bar is a 2 by 2 matrix with elements 0, 1, minus 2 and 3. First, we find the eigenvalues by subtracting lambda from each of the diagonal terms and setting the determinant equal to 0, equation 1.51. If we look at equation 1.51, we will subtract lambda from the diagonal terms. Then to find the determinant of a 2 by 2 matrix, we will multiply the diagonal terms and subtract it from the off diagonal terms and set the determinant equal to 0. This is exactly what we have done in equation 1.56. We will subtract lambda from the diagonal terms. Then we will multiply the diagonal terms and subtract the off diagonal terms. If we multiply the diagonal terms, we get minus lambda bracket 3 minus lambda minus off diagonal terms, which is minus 2. This makes it minus lambda 3 minus lambda plus 2. If we carry out the multiplication, we get lambda square minus 3 lambda plus 2 is equal to 0. Solving this quadratic equation yield two eigenvalues. We have a quadratic equation, so we will get two values of lambda. We will apply the formula lambda is equal to minus b plus minus under root b square minus 4ac over 2a. The value of a is 1, the value of b is minus 3 and the value of c is 2. If we substitute the values, we get two values of lambda. Lambda plus is equal to 2 and lambda minus is equal to 1. To find the eigenvector corresponding to lambda plus is equal to 2, we know that equation 1.52. In equation 1.52, we have subtracted the value of lambda from the diagonal terms and have done matrix multiplication with the vector with components xa1 and xa2. Similarly, lambda plus is equal to 2. We will subtract plus 2 from the diagonal terms and carry out the matrix multiplication with the vector with components x plus 1 and x plus 2 and set it equal to 0. This yields two equations and two unknowns. We will carry out the matrix multiplication with the vector and we will get minus 2 x plus 1 plus 1 x plus 2 is equal to 0. The second equation would be minus 2 x plus 1 plus 1 x plus 2 is equal to 0. Both the equation in equation 1.61 give us the result that x plus 2 is equal to 2x plus 1. Notice that these are the same equations, so we solve it to obtain x plus 2 is equal to 2x plus 1. An eigenvector corresponding to lambda plus is equal to 2 is thus x plus is equal to a vector with elements x plus 1 and x plus 2. Since x plus 2 is equal to 2x plus 1, we will substitute that. Then we will take x plus 1 in common and we will get a vector with elements 1 and 2. We are getting the vector in terms of x plus 1. To obtain a unique solution, we need to normalize it. We will use equation 1.54, which says rho xa1 conjugate xa2 conjugate times vector xa1 xa2 is equal to mod xa1 square plus mod xa2 square, which is equal to 1. We normalize this using x plus 1 square bracket 1 square plus 2 square is equal to 1. This gives the value of x plus 1 is equal to 1 over under root 5. So, one eigenvector pair is lambda plus is equal to 2, x plus is equal to 1 under root 5, vector 1, 2. The eigenvalue is lambda plus is equal to 2 and the eigenvector is x plus is equal to 1 under root 5 column vector 1, 2. If we repeat the procedure for eigenvalue lambda minus is equal to 1, we'll subtract the eigenvalue from the diagonal elements of the matrix. We are left with the 2 by 2 matrix with elements minus 1, 1, minus 2, 2. If we carry out the matrix multiplication with a vector with elements x minus 1 and x minus 2, we get two equations. Minus x minus 1 plus x minus 2 is equal to 0. Minus 2x minus 1 plus 2x minus 2 is equal to 0. Both these equations are the same. They give us a result that x minus 1 is equal to x minus 2. Since x minus 1 is equal to x minus 2, we get the vector with elements x minus 1, x minus 1. If we normalize it, we get x minus 1 whole square plus x minus 1 whole square is equal to 1. This gives us 2x minus 1 whole square is equal to 1. X minus 1 is equal to 1 under root 2. Therefore, for the eigenvalue lambda minus is equal to 1, the eigenvector x minus is equal to 1 under root 2, column 1, 1. The eigenvector corresponding to lambda minus is equal to 1 is found in similar fashion. It is x minus is equal to 1 under root 2, column vector 1, 1. Thank you for watching. Allah Hafiz.